But remember, we're going to use virtual threads, so we don't care. We can just write simple and blocking code. But this virtual thread is not just some arbitrary thread somewhere in some pool doing some task. No. This was created as a child, as a subtask of something else, and that something else is this. But also that means that instanceof checks in that hierarchy are not a code smell anymore. Welcome everyone to the Inside Java Newscast, where we cover recent developments in the OpenJDK community. I'm Nikolai Parlok, Java developer advocate at Oracle, and today we're going to do something a little different. Usually I just talk to you and maybe show some code on the side, but you can totally just listen to an episode while doing laundry or preparing lunch. But not today. Because Java 19 is coming out in 12 days and I really want to show it off. But I already talked you through all the features back in June. So today we're going to get our hands dirty and code up a little GitHub crawler that uses virtual threads, structured concurrency, and data-oriented programming to create a little page tree. So sit your butt in a chair or couch and look at the screen. Ready? Then let's dive right in. Okay, let's go. We first review our goals, and then we're going to see what we already have, and then we're going to take it from there. So we start with a seed URL that points at a GitHub page. And then we want to look through that page and gather all the interesting links. And interesting links are not all of them, but a certain subset. And the certain subset is the GitHub pages that we understand, which at the moment are just issues and pull requests, and then all kinds of external pages. Then we want to resolve them, get their HTML, go through their interesting bits and their links, and then keep going like this recursively until we hit a certain depth, so we don't end up scraping the entire internet. Okay, and the types we want to create is a small little type hierarchy that we're going to look at in detail later. For now, the important part is, at the root of this type hierarchy is the page interface, which just prescribes a URL, and that's it. And so how do we get these? We have a page factory here, and the page factory gets as input a URL and the HTML that was scraped from that URL. And then it does some HTML parsing, figuring out important bits, figuring out which type to create. Is it the GitHub pull request page or an external page? All that stuff. We're not going to look into that because it's not that important for this demo. In the end, what it will spit out is a page with links. And a page with links is the first interesting bit here. Since we have records, which are named tuples, we're going to have situations where we just want to bunch some data together occasionally that we can do really well with records. And this is also where we can start. Because if we look at this record is probably not supposed to contain a null page or a null set of links, and I already know that it's not supposed to contain a mutable set of links. So let's make sure that's not the case. Record has a feature that's called a compact constructor, which makes it very simple to apply some checks. And then also something that I already know is that there are certain situations where we don't actually have the links set yet. We can take a look at this constructor, and we will see that we have this call here, which doesn't have links at the moment. So sure, let's kick that out. Let's create a constructor that doesn't need that. The interesting bit about this is this is an immutable set, and then this copy of operation does nothing because it sees it's one of these immutable sets, so unmodifiable I should say, and then it won't create an actual copy. Okay, so that's a nice little start, and we can now keep doing something similar for some of these other types. And that's that. One thing I do want to point out here is the formatted thing. So I'm using a string here that I want to format some information, that I want to put some information in. Basically, string interpolation, which Java doesn't have yet, but may get in the future. Anyway, so since Java 15, I want to say, there's a method called formatted, which works exactly like string.format, but it's non-static. So you can just append it to the string that you're writing. Okay, so now let's start writing some actual code and let's use some virtual threads. So what we want to have eventually is a page tree with the root page at the top and then all the other pages that references to below. Or there can be backlinks, so it's not technically a tree, but let's ignore that. And the page factory that we have only creates a single page and then also contains all of the links. What we now want to do is we want to resolve those links too, in the end put together this page tree almost. So let's do that. Let's create a specific type just for that, that has that task, and that also then start with writing a method that has the correct signature, and then we can take it from there and fill that in. Okay, so let's start with having a page tree factory. Page tree factory. That looks Right. Okay, so let's start doing that. First thing, I'm gonna use Java 11's HTML API, HTML client, to connect to that page, to that URI, and fetch all the content. So I'm just gonna do that and shut up for a while. Now here's where it gets interesting. What kind of request do we send? We can send a blocking request, or we can send something async. And the common wisdom would be, now let's do this asynchronously, let's get back some futures, let's append computation there. But remember, we're going to use virtual threads, so we don't care. We can just write simple and blocking code. So I'm just going to use the send method here, because it makes everything else a bit simpler. Now we should reuse a client. Always using a new client is not great. So let's have a field for the client. And for now, I'm going to make this public so we can see whether that works as expected. So let's do this in main. You know, you should write tests, I know, later. There we go. Okay, took a while, but that's some HTML. Okay, neat. So that part worked. Now let's keep going and let's pour this HTML into the page factory that we have. So let's talk about error handling. The interrupted exception indicates that this is a blocking process. So I definitely want to keep that one around. But the IO exception, and more general, all kinds of exceptions that can happen while loading the page, I do not want to keep throwing. I instead want to encode in the result that there was a mistake, that something didn't go well, and that's why I have this error page type here. So for these, I want to return error page instead. Now let's run this. And there you go. Got the pull request page right here. Great. Now let's start resolving those links that come with that we've ignored so far. Let's fill in this here. For that, we go back to the page tree factory, and we now have to handle those, right? So we have this for links is this stuff. Let's resolve these links. I'm going to write the outline of the method, and then we're going to fill it in together. Okay, assuming we have the method already, which once again we're going to look at in a second, what do we do with those? Well, we cannot assign them to just any kind of page, because not every page actually has children. And if you look through this hierarchy, we're only interested in following up links of known GitHub pages. So only GitHub pages has these links set that we can fill in. So we need to have an instanceof check here to make sure that we add it to the right type. And now it's time to resolve these links. So what we want to do eventually is we want to, when we resolve one link, we can actually recurse and say just create page. Really, that's mostly what we want to do. All right, so in effect, what we want to have is this kind of a loop. And then would collect that in a list set and return it. But that would mean that we would block, right, on the first call, on the second call, on the next call, and that would be okay. But hey, why not run all of them at once? And this is where structured concurrency comes in. We can not only easily start all of these at once, we're also going to make sure that we start and end that concurrent block in the same block of code. And that, as you will see in a second, will give us additional information when we start debugging this. So I'm going to start using the structured concurrency API. We're going to start with the try with resources block. Because that's the best way to use this to make sure that, that the scope is closed. And we're going to create one of those scopes. So that's going to be a StructuredTaskScope. And we're going to shut down on any failures. There you go. And then we're going to catch the execution exception that it throws. We're going to see later what we do with that. What's the complaint here? Oh yeah, right. A new would probably be helpful. Okay, neat. Now, we start with this loop, basically, but instead of doing this exactly as is, what we're going to do instead is, we're going to take this scope, and we're going to submit a task to the scope. And the scope submit, no, it's not fork, it's fork, so we're going to fork a task in this scope. And that's callable, so we can just say here, create page, URL, and on the step that we're at. All right, so that's a link. Okay, what we get back here is actually a future of the page. So this is the link, let's call link future. And we need to collect those because we later want to make sure that we get all the results. So let's create a list of those. So now what we're doing is we're going through all the links that we have, and for each of them we scope a new task and we put that into the children list. Now comes the interesting part. We're done with spawning all the tasks. Now we want to wait for them to be finished. All right, so we say scope.join. And join, because it's a blocking operation, once again can throw interrupted exception, which is fine. We can throw this to a method signature. There's that. And that was actually a mistake by me. The error we got up there was because I lacked the new. But this will be thrown now because we also should always, like in almost all cases, you want to do a throw if failed. So we're basically checking, did any of these tasks go wrong? If so, this is what shutdown on failure means. If any of them goes wrong, the entire scope is shut down. All threads get the signal to shut themselves down. They don't do magically, right? The code in there has to check for that. But anyway, so it shuts down, then the exception will be thrown here. And that is under the assumption that as soon as one of them fails, we want to shut everything down. Which we kind of expect not to happen, right? Because we created that error page earlier. So we're basically saying, look, if it's an expected kind of, like it's any kind of error, we really want to create an error page instead. So we're kind of not expecting this to happen here. Okay, what do we do next? Well, now we can just say, now we're gonna turn this children thingy. And the futures have a method that's called result now, which you're basically implying with that is, I know I already waited for the result, which we did because we said join here. Right, so join means, like, you know, wait for all of these to complete, so the result should already be there. Get this, we turn this into a list, and we can return that. And now here, as I said earlier, we're not expecting anything to happen, so let's just throw a new illegal state exception. If I want to run this, I'm probably going to get into trouble because the depth here, it's decremented here when we go into this. And then it's further past n, so it's decremented, but probably we should check whether it's 0. That will probably be helpful. We should probably add some messages here so that we can see what's going on. Okay, let's give this a try. So what we'll see here is we're resolving this, and then we're doing it again somewhere here, 627, and then again somewhere. We'll see another 627 somewhere. There it is. And then, because as I said earlier, these things backlink, so that's not a good idea probably. Because we're going to resolve the same page over and over and over again. Each of those resolutions will end up in different objects, so that's not great. So what I'm going to do now, which is not essential to the whole structured concurrency and data-oriented programming story, so I'm going to, you know, skip past most of what I'm doing now. I'm just going to add a little bit of optimization where we check, did we already create this page? And if yes, let's not store the new instance, let's keep reusing the old instance. But I'm going to have a little bit of observation about that in a second. Or rather, it's actually a question that I didn't get around to verify. So the question now is this. There's this compute if absent on concurrent maps, right? And what you're saying is, check if that thing is there. And if it is there, don't do anything. But if it's not there, run this computation and then put the new result in there. And what this does is, in our use case, since we first check whether something is in there, and if it's not in there, we're going to create it, but we're not going to put it in there if somebody else in the meantime already placed it there. So the idea is 2 threads could come and see that the page is not already resolved. One of them finishes a bit earlier and is the first one to put it into concurrent hash map, and the second one will just have its work wasted, which is a decent way, you know, to structure this. Now the question is, couldn't we in compute if absent actually do the resolution, right? This like fetch the page with links. We could do this technically in compute if absent, which means check if the map page is there. And if it's not there, run the entire blocking operation that, so I mean it takes a while to resolve that page and then put it into the map. This could actually be the better solution because it wastes this duplicate effort. Why I didn't do it here, and I would have to look that up, is because I think the concurrent hash map has to lock part of a map during this computation, and I'm not sure whether that's true. But if it is true, then you probably don't want to let it lock for a long time while you're doing like an expensive computation. But that's like basically some kind of optimization. This code works correct. The other code would actually probably also work correct. It's just a question of which of these would pan out which way when you're doing this, when you're trying to optimize this. Which this is not about, so let's not focus on that. But what I just did is I made sure that every page is just added, like there's one canonical instance for each URL, and that's the one in the map. And if a second page gets created for the same URL, it is discarded. And I actually think that this should now be it. Let's try to run this. You know what? Actually reduce the depth to make this a little bit quicker. And we got an error. All right. Yes, we got an error. And the error we get is something hashcode. So look at this. We had a stack overflow error during the hashcode computation. What's going on here? Well, look, we're going to the GitHub issue page. Let's have a look at that. And you will see that it doesn't have a hashcode or string or an equals implementation, which means it uses the default implementation that the record creates, which is based on all the fields. Now the issue with that is all the fields includes the links. And all the links include all the other pages. And then there are backlinks, which means the link can go, you know, back to the page where you started the hashcode colon, or equals actually the same thing. So you quickly run into a cycle. And that causes the stack overflow error. So what we need to do here is we need to have a more reasonable hashcode and equals implementation. And we already have something which is, you could almost describe as a unique identifier of a location or of a resource here. So, you know, why not use that for the hashcode? That's also, by the way, why I don't use the URL type, because the URL type actually resolves for hashcode and equals computations, which, anyway, so that's why I'm using URI. Okay, so let's implement a hashcode function, and let's implement a cool equals function. That's pretty good. Look, I'm gonna pull out some of the stops that Project Amber has given us, because the old way to write equals is still valid if you have a dependency hierarchy and you want to compare on get class specifically, but record is final, so there are no elements below that, so we can actually get away with instanceof, which makes it so much shorter. So how does a usual equals check work? First, and this is basically performance, not basically, it is a performance optimization. You compare to yourself, just because that's faster. So if it's this other, then we're already done. Otherwise, we want to check whether it's the right instance, and that's simple now. So let's say other instance of, and if it's also an issue page, we just need to compare whether the URLs are equal. And that's all. That's the entire check. Null elements are also discarded because null does not pass the instanceof check. So this is all you need. There's no additional variable. There is no casting. There is no, you know, sequence of ifs. It's just this one thing, which I think is really cool. And for the hash code, we're just going to use the URL as well. And then I'm going to keep repeating that in all the other pages so that we get the correct behavior everywhere. Okay, now this should work. Which it didn't. We get something else that looks, oh my god, eerily similar. Would you look at that? Stack overflow error, but this time it's in a string builder, blah blah blah. It's into string. Alright. This print here prints the page to string, again uses all the fields that recurses, blah blah. Same thing as just now, so I'm going to apply the same fix. Next try. And there we go. Nice. Did its thing. And we have a bunch of children now, probably, as well. We don't know that. We didn't check. So let's actually check that. Let's go into main, and just for the root page, let's also print. All right, haha. What we get back here is a page. We don't know whether it's a GitHub page, and if it's not a GitHub page, as I said earlier, we're not interested in any children, any links that it has. So we don't have that as a field. So that's fine. So let's say if the page is an instance of GitHub page, and if you like running down, if you have like shivers running down your spine of all of these instance of checks, we're going to talk about that in a second. Why that is not such a problem as you would think it could be. There we go. We have the GitHub page, and then we have an external page, and a GitHub PR page that's linked from there, and an external page, and more blah blah. So apparently there's a bunch of stuff linked from that thing. I want to do something else though. I want to show you something something really cool, which I said earlier. We built this. We use structured concurrency to start this task scope here and end it here. So that means every task, every virtual thread that starts in this scope is clearly part of the overall task. So the overall task is resolve these links, and then each of those links is a subtask of that. And the funny thing is, each subtask recurses into create page, which then also resolves links and does the same thing again. So we don't just have like two layers. We have like one layer where we start with the first page, and then for each link we have a scope with one thread for each link, and then so on and so forth. The scopes, as how they are created and how they are closed, still follow this tree structure, and we can actually observe that. We need a thread dump, which we can create with J command. The command line for that I have on my clipboard here, and now I'm gonna fill in the process ID and put the process to sleep for a couple seconds so we actually have time to execute this. Okay, let's give this a go. Okay, and now we have a new file, threads.json here. Let's see what we have. Okay, so this is the thread time as a JSON file, and now we can start to go through this. You have a bunch of containers here. Let's collapse these containers, and then we probably can see some structure. Okay, so we have a root container here. Then we have something is like the fork join pool, and so where is it? There it is, the fork join pool, and a couple other ones. But the interesting thing are the thread flocks down here. Let's have a look at one of those thread flocks. So we can see here that this is our code, page tree resolve links, that's here, and then runs into the StructuredTaskScope stuff, and at the moment it's yielding on something, so probably it's waiting for the HTTP client to return. It has a thread ID 83. The interesting thing is it has an owner, which is 1, and that should probably be 1, the main thread. So the main thread owns this specific thread flock. We have another thread flock here, which has one of the threads has ID 110, and that one is owned by 38, and 38 was the one that we just had here. So what that means is, if you have take a heap dump and you're wondering like, why am I here, for example, not only can you track this up all the way to eventually your code, you can then also, from there it just becomes uninformative and you end up here. And this is where it usually ends. But what you can do now is you can see, wait a moment. But this virtual thread is not just some arbitrary thread somewhere in some pool doing some task. No. This was created as a child, as a subtask of something else. And that something else is this. So now we can go to 38. And check, okay, so what's 38 doing? Oh, it's doing this. So if you have like a deeper structure here, you will be able to, from any kind of breakpoint that you hit, once IDE make this navigation easy and offer this information, you can then, from any breakpoint you hit, navigate all the way through all the task scopes that surround these individual tasks, go all the way up potentially to your incoming web request that triggered this, this structured concurrency approach to solving the specific issue that the code is trying to solve. And that's great. Like, this is such an additional amount of information that will make it easier to understand what state your system is in a situation where you hit a breakpoint, or when you take a thread dump, or anytime you want to figure out what really is going on. This will be invaluable information. And that concludes the structured concurrency part of this little demo. So let's close all of this down. And let's take a little break. So, what have we been up to? Yeah. I hope nobody was talking to their screen. I can't actually hear you. Okay, let's have a look at some data-oriented programming here. So for that, I want to catch up on something that I promised you earlier. I want to have a quick look at the structure here of these types. Specifically, I think these ones are the interesting ones, and that one. Okay, so let's start with a page. That's, as I said, as a URL, but that's the top of the interface hierarchy, or of the type hierarchy. It permits two kinds of subpages. It could be an error page or successful page. Kind of makes sense. An error page comes with an exception on top, and the URL, of course. And a successful page, that's a further interface that can have some content. As I mentioned, content not yet filled in. Forgive me for that. And it permits further pages. So a successful page load could either be an external page, which is, just some content in the URL, or it could be one of those GitHub pages. And the GitHub pages, they have links, because we're only interested in further links on these GitHub pages. That's why they're not modeled elsewhere. We also have this nifty little subtree method here that gives us a stream of all the pages that are from a specific page in that tree plus backlinks are reachable. That are reachable from there. So only GitHub pages have links, and then we have to do specific implementations: GitHub issue page and GitHub PR page. And so this is expressing information in the type system. We could just have one type, which is called a page, and then you would have like a page type enum. And only if the page type enum is that, could you expect the link set to be non-empty and all of that. But that's not great. You want to get the compiler on board with the structure that you're creating. And sealed interfaces and records make that really easy. Sealed interfaces, or sealed types in general, because you can make sure that only legal states are representable and nobody can just add additional types in a type hierarchy. And then records, just because they make it pretty concise. And since we use sealed types, we'll be expressing that we are aware of what kind of implementations there are. And if it comes to that, then the compiler can help. I can show you that later. But also that means that instanceof checks in that hierarchy are not a code smell anymore. All they really mean is, I know what the type hierarchy looks like, and for specific operation, I need to know where in that type hierarchy I am, and then I'm going to call the corresponding methods. So what I want to do is I want to create some statistics. So let's start with that. To evaluate that, the statistician needs a method that's very simple. It's like public static I give you back statistics for the root page that you give me. It's a root page here. Okay, that's that. And because we are going to go through all the pages and we're going to count something, one easy way, it's not the only way to do this, but one easy way to do this is to just create a specific statistician instance, which has some mutable state that just does the counting, and we're going to use that for to create the statistics instance. Okay, so how are we going to do this? The root page that we get does not necessarily have children, right? We already covered that. Only if the root page is actually an instance of GitHub page can it even have kids. So now let's increment those stats. So how do we do this? We need to figure out what kind of page we have here. And this could be a series of instanceof checks, but of course you know what I'm going to say. I'm going to say, no, let's switch over the type and let's use type patterns here. So let's say in case it's an error page, you don't even need the page. In that case, what's going on? Oh, we need the type. In that case, number of error pages needs to be increased, and the same for all the other kind of pages. Now note that if this switch is not complete, I do get a compiler error. So the compiler wants me to list all types. In this specific case, I actually do need to list all types, but there might be cases where I can also use a default. I would recommend not to use the default until you really want to say whatever new types are ever created, I don't care about them. You'll see that later, how that comes into play. But generally speaking, enumerating all types explicitly is probably a good default approach to this. Now let's call this. There it is. Okay, So we pulled 5 issues, 8 pull requests, 11 external pages, and no error page. That's always good to know. Now let's do something similar and just have like a nice little output. I create the outline first and then we can fill in the interesting bit together. Okay, at this point we're gonna repeat something that we just did. We're gonna just switch over the pages and then we already know which cases we are, so we're gonna steal those. Then we just figure out what we want to print there. So let's take this. Because we can immediately return the result because switch is an expression. Nice. And now we just add some information here. And there we go. We create like a bunch of little outputs here. And we took in specific information from these types, right? So if it's a pull request page, we want the pull request number, we can only get that if we know it's a PR page. You know, otherwise that wouldn't make any sense. So what we're doing here is we're breaking it down to the specific type and then extract information that only that specific type has, as opposed to like overly general information that like some kind of shared super type has. And this is what the structure of sealed types and using sealed types really is about. Expressing the different kinds of information, of data, of input, of output that you have as different types, and then using switch and maybe even deconstruction. We could actually use deconstruction here. You know what, let's just for fun, let's use this deconstruction here. I'm sure that's gonna work out on the first try. Should we give it a try? Not sure why IntelliJ says this is unreachable, but just one way to figure it out, I guess. This seems to work for me. It feels like this is a mistake in IntelliJ's code highlighter, because it definitely gets to pull requests. So I'm not sure. Like, this is not like the compiler is happy. Like if this, so IntelliJ says this switch label is unreachable. But if that were the case, then A, we would not see that output, which we do, and B, the compiler would complain if that clause dominates the next one. I'm not going to use deconstruction here because those are too many variables and I don't have to. Like, I can use it this or that way. And I know that just ended up on a massive sidetrack. What I actually want to tell you that this kind of approach lets you encode assumptions that you have in the type hierarchy, which gets a support by the compiler, and all this looks good and all, but then the question is, isn't this unsafe? Isn't this like risky? Like when I change the code, how does this behave? That's like the feeling why we think like instanceof checks are bad, right? Because what if they're new types and what will all of these checks do then? And this is the critical understanding why sealed types are so essential to this. They're not just like a little bit of thing that you can add here, but they're crucial. So let's say I want to add something like the issue page. Let's say I want to add a new type and I'm going to call it the GitHub commit page. Okay, so I wrote the code. I can now parse the commit page. And then the commit page will probably not have an issue number, but there will be a string of a commit hash, right? Let's say this one should probably not be null. Oops. And there we go. Okay, done. But look, we get a compiler error. Compiler what we get here is commit page is not allowed in the sealed hierarchy. Okay, so GitHub page does not allow the subtype. Well, that's easy enough. Let's edit, right? Let's edit the commit page here. And if we do that, and we try to run the program again, why does it run? Oh, there we go. What? Did IntelliJ recompile? The heck is going on? Now we get the compile error. Why does it keep running? What am I doing wrong? Because clearly this is very weird. So IntelliJ discovers the compile error here, as it well should, because this is an error, right? So this switch expression does not cover all input values. That's what I was going for. That's what I wanted to show you here as well, right? So wherever you switch over the super type, now it's not exhaustive anymore. So when you do add a type, the compiler will pinpoint where exactly you need to change stuff. And that was why I said earlier, so let's say we just count number of GitHub pages here. So that means you have two different types that trigger this, right? You can have GitHub PR page that increases this, and the GitHub issue page. And you could think like, you know what, let's put this into a default. So because I got the first two cases here, and then for default, I want to do this. And that works, but this, well, you know, that variable doesn't exist, of course. So let's just put it here for a second. This works, but now you do not get a compile error when you add an additional type, because the additional type will silently go into the default. And it's not clear whether that's actually desired because you don't know what types you're going to add. So that's why I said earlier, I recommend to not use default and instead explicitly list all the cases that you have, so that you do get this compile error that says, hey, look, this new type is not covered, which should then lead to the program not executing. I don't know what IntelliJ is doing here. Like, it seems like it's not recompiling. Does it have something to do with this? I want to try to fix this. Okay, now we get a compile error. Not sure what's going on there, but the point is, now we finally go to the commit page. Now we finally get a compile error because of the commit page, because it's not covered. And that makes it safe. That's what the visitor pattern usually achieves, right? It allows you to combine a type hierarchy with a number of different kinds of functionalities, and combine them in a way where every type implements each function, or rather each functionality is implemented for each type, without having to add the functionality as a method on the type, in this case on page, which we presumably don't want, and B, still leading to compile errors that will definitely lead you down the path to update all functionalities for all new types whenever you add them. And there you go. That's the presentation. Let's kick out the commit page again, and let's have one more successful run towards the end. Probably there's a compile error somewhere here now. No. Oh, right. When I delete the type, IntelliJ delete that one as well. Good. We're making friends again. And that's it. That's the demo. In goes virtual threads. Out comes data-oriented programming. And that's it for today on the Inside Java Newscast. If you haven't already, check out my feature rundown of Java 19. And if you want to take a look at the code, there's a link to the demo project in the description. While you're down there, ask any questions you have, or let me know what you think about this coding-centered format. And don't forget to like, subscribe, hit the bell, share this episode with your friends and enemies, and sacrifice a goat to the YouTube algorithm. Something special is brewing for you in 2 weeks. So long!